All right. Welcome, everybody, to this week's iteration of GOCC. We're very happy to have Ben Grant, who's going to be talking about understanding the complexity of infinite quiver properties and mutation sequences through topology. Just before we begin, I'd like to reiterate our community statement. So we are all learning, everyone has something to contribute, and no one has all the answers. So with that being said, take it away, Ben.
All right. Well, thank you so much, Joe, for the introduction, and thank you to the organizers for the invitation to speak. Really happy to be here. So today I want to talk about some infinite combinatorics. I want to talk about specifically the combinatorics of infinite quivers, which we'll get into what those are, and mutation sequences on those guys. And we're going to take sort of a topological perspective to these things. It's going to be, it's going to be kind of fun, honestly. I like this way of thinking about infinite combinatorics, and hopefully I can spread some of that enthusiasm as we go. So maybe just to get started here, just a little bit of a sketch of what I want to go over. First things first, I sort of just want to talk about some basics on quivers and quiver mutations. And I want to spend also some time talking about a couple of topological spaces that are sort of the key focus of what I want to talk about today. These are going to be our spaces LF and AF. Those stand for locally finite and aerofinite quivers. We'll see what those are in just a little bit, but that's where I want to start. I want to start with quiver mutation combinatorics and look at what that looks like if we try to topologize it a little bit. And then I want to talk more specifically about some of the things you can do with this approach. So the second part of the talk, I want to talk about specific properties of quivers with respect to mutation, without respect to mutation, viewing them as subspaces of these two topological spaces, LF and AF, or spaces that come from these guys, like they're squares or whatever. Right, I want to talk about sort of this point of view, and we're going to see that this is something that we can do that naturally lends itself to a very interesting notion of complexity. Right, we're able to use this tool from a branch of mathematical logic called descriptive set theory. We're able to use this tool called the Borel hierarchy and talk about, hey, this set is more complicated than this set, right? And so there will be some interesting things we can say about properties of quivers in that language. From there, I want to shift a little bit to infinite mutation sequences. So again, we'll see what mutations are in just a second, but the rough idea is that sort of a dynamical kind of operation we can perform on quivers, and with topological spaces, we can talk about limits of things. And so why don't we talk about, what it means to take an infinite mutation sequence and look at where it converges or diverges or that sort of thing. And then at the end, if we have some time, I want to talk about sort of an open question that maybe relates sections 2 and 3 a little bit more, sort of takes the approach of section 2 to questions of section 3. Cool. And if anybody has any questions at any point in time, feel free to just interrupt. I'll do my best to see if there's anything in chat or anything like that, but feel free to just unmute yourself and interrupt me if you need. Okay, so first things first, I want to talk about these spaces, LF and AF. And of course, quiver mutations as well. Oh, it looks weird in the PDF. Oh no. Okay, well, that's all right. So what's going on here is we have these things called quivers. And if you know what a quiver is, fantastic. If not, it's a pretty straightforward idea. It's a directed multigraph. It's a quadruple of two sets, Q0, Q1, and two functions, S and T, both of them from Q1 to Q0. Q0 is thought of as a set of vertices. Q1 is a set of arrows. And S and T are source and target functions that take an arrow to its source vertex or its target vertex, respectively. Okay, and then for this talk, throughout the rest of the talk, I'm going to assume that all of my quivers have no loops, which are arrows that start and end at the same vertex, or oriented two cycles, which are pairs of arrows that have opposite source and target with respect to one another. Okay, and so here are some examples of quivers. I've numbered them. I've numbered the vertices, 1, 2, 3, 4. In all of these cases, they have at most 4 vertices. And I also have just taken the liberty of not labeling the arrows, except for when I have numbers on them. That means that actually I should be thinking about this as, for example, in the left example, 2 arrows from 1 to 2. right? So I'm thinking about this as a multiplicity of arrows. Or in the second example, I have 4 arrows from 1 to 2. I don't really care about the identities of the arrows specifically. I just care about how many there are. So it's okay to sort of collapse these down into just numbers. Okay, and then quiver mutation is an operation we can perform that takes a quiver and sort of transforms it in a local way into another quiver. So what we do is we take a vertex k in our quiver, and we can define the mutation of q in direction k according to this 3-step process. So the first thing we do is we say, hey, for any pair of arrows that passes right through our vertex k, right, starts at some vertex I, we have an arrow from I to k, we end at a vertex j, we have an arrow from k to j. Right, what we're going to do is we're going to cut out the middleman. We're just going to add an arrow straight from I to j. All right, and then after that, after we've done that as many times as we can without doing it twice, for any particular pair of arrows, we're going to reverse all arrows incident to that vertex k. So for example, the arrows we would see in step 1, right, the arrow from I to k would become an arrow from k to I. The arrow from k to j would become an arrow from j to k, so on. And then finally, we might have in step 1 added arrows in the opposite direction of existing arrows. So we might have accidentally created oriented 2 cycles, in other words. And so we don't like those, so we're going to cancel them out in pairs, right? We think about one arrow this way and an arrow this way as sort of annihilating each other, right? And so just as an example, I have an example of a quiver at the bottom. It's the same as the very first example on the left in the top of a 3-vertex quiver, and I'm mutating it at vertex 3. And so that's how I get to this quiver in the middle. And then I can mutate that guy at vertex 2 and get to this quiver on the right. And so importantly, this is something that matters very much when we're talking about the combinatorics of quiver mutations. So that mutation at a vertex is an involutive operation. So if I mutate at a vertex, let's say 3, and I mutate at vertex 3 again, then I'm back where I started, right? And you can confirm this by doing these examples out if you like. So that's why I've drawn these squiggly arrows with mu3 and mu2 over them as 2-sided arrows. Right? It's because I can do the mutation to get back. Okay. Cool. So from here, right, maybe a quick change in perspective, if you like, is we can think about at least quivers on n vertices as skew symmetric matrices with integer entries. And so what I mean by that is if you have a quiver Q and you take 2 vertices I and j in Q, you can take the signed number of arrows from I to j. And okay, because we have no loops or 2 cycles, oriented 2 cycles in our quiver, the signed number of arrows is always just going to be positive or negative the number of arrows from one vertex to the other. There's never going to be any like, oh, I have 3 arrows this way and 2 arrows back, right? The signed number of arrows is just, if I have 5 arrows from I to j, I have positive 5. I have 3 arrows from j to I have negative 3, so on. And I can collect those up into a matrix. We call that B sub q. And so if you like, you can go through the 3-step process we just did and translate that into this matrix language. And you get the following, right? You see that mutation is defined in sort of this way, where we can take B sub ij prime, right? This ijth entry of the matrix corresponding to the mutation of Q at a vertex K. It's this sort of piecewise expression, right? And here I've taken the liberty of including some brackets with pluses on them. This is just a shorthand notation for the maximum of whatever's inside with 0. We also call that the positive part, if you like. And so the reason I'm writing this down here is there's an important observation we can make, which is that this only depends on sort of local information, right? If I've got a vertex K and I want to know what Bij prime is, right? I don't really need to know very much information to be able to compute that, right? Okay, first of all, I mean, I have to know if I or j is K, so I know which case I'm in. But let's say I'm in the second case, I only need to know 3 pieces of information: Bij, Bik, and Bkj, right? And this will still work even when our quiver has infinitely many vertices, right? This is a very local operation. Of course, to make this work, like these have to be numbers, right? So I can't just like say, oh, I have infinitely many arrows from one vertex to another, right? Because that doesn't really make much sense when we're trying to use this formula. So we can't do that. But as long as our arrow multiplicities between 2 vertices are finite, for all pairs of vertices, then we're happy, right? And if this is the case, we call this quiver a quiver with this property. We call it arrow finite. Okay, so this is nice, and already like this is a class of quivers that we can do mutations with, even if they're infinite. But there's sort of a smaller class of quivers that has nicer properties in some cases, especially if you like representation theory. Not going to talk about that today, but there is sort of some background there why you would care about this following property of local finiteness. So what does this mean? This means not only are we arrow finite, right? The number of arrows between any two vertices is finite, but also the degree of any vertex is finite, right? So if I take a vertex and I look at the total number of arrows incident to that vertex, that's a finite number. And so we have arrow finite quivers, we have locally finite quivers. These make sense for quivers of any cardinality. But in what follows, I'm going to restrict specifically to just countable quivers. And so in this case, I'm going to think about quivers whose vertex set is the natural numbers, right? Typically, I should say we like thinking about finite quivers and finite quiver mutation combinatorics. But when you try and take a topological point of view on that, it doesn't work out as nicely because there are only countably many of those guys. But in this case, if we have countably infinite quivers, we can do some interesting topology. So let me say a little bit about what we're going to do here, what the big idea is. So we have these definitions of arrow finite quivers, locally finite quivers. We can collect these guys into topological spaces. So, I mean, okay, first of all, we need sets of these guys. So let's take sets of these guys. Let's let AF be the set of all arrow finite quivers, whose vertex set is the natural numbers. Let LF be the set of all locally finite quivers, whose vertex set is the natural numbers. So far, these are just sets, right? I'm just collecting things into sets. And now I want to topologize them. So what do? I say, hey, let's put topologies on these guys by finding some bijections with these guys to something that I already sort of know a topological structure on, right? And so what that looks like for us is this space n to the n. This is the space of all sequences of natural numbers, if you like, or equivalently functions from the natural numbers to the natural numbers. This is a topological space with cardinality of the continuum to the LF naught. And it's got a very natural topology given by taking the product topology of countably many copies of the discrete space n and taking their product. Right? Importantly, this is not a discrete space, despite being a product of discrete spaces. If we took the box topology, that would be a discrete space. That's not what we're doing here. So, all right. So I said that we want to find bijections between AF and LF with this space, n to the n, and then pull back the topology on n to the n onto these sets to give them their topologies. So that's exactly what we're going to do here. So for AF, I'm going to ask you to fix your favorite bijections from the integers to the natural numbers. And I'm also going to ask you to fix your favorite bijection from pairs of natural numbers to the natural numbers. I've written that in sort of angle brackets there. It's sort of like a pairing function if you want. And then, okay, given a quiver in AF, or an arrow finite quiver with vertex set n, you can define its image under this map that I claim is a bijection in n to the n by saying that, okay, when I take as input a natural number that really I should be thinking about as coding a pair of natural numbers, ij, what do? Well, I take the natural number that really I should be thinking about as coding the integer number of arrows from I to I plus j. Now, why I plus j instead of just j? Well, if I did I to j, then, okay, I'm kind of double counting in a way, right? Because if I have, angle brackets I comma j and I plug that in, and I plug in angle brackets j comma I and I plug that in, and those tell me things about bij as opposed to bi I plus j, then I'm not really like, it's redundant information. And in order for this assignment to be bijective, I want to eliminate redundancies, right? So that's why I have this I comma I plus j, right? I only am learning information about the numbers of arrows between some vertex and some vertex of higher label, right? That way I never repeat myself. Okay, and so on the other side of things for LF, I'm going to ask you to fix your favorite bijection from the integers to the non-negative integers with the property that h prime, I guess I called it here, h prime of 0 is 0. And then for your favorite quiver in LF, your favorite locally finite quiver with vertex set n, you're going to define its image under this bijective mapping as this weird product of primes to these h prime of bi I plus j powers. And this is why we need h prime of 0 to be 0, because, okay, if bi, I plus j is 0, right, then I don't want to see any copies of the prime pj popping up here. This is what actually like gives me a natural number here, right? As is, this looks like an infinite product over infinitely many j. But since Q is a locally finite quiver, only finitely many j give you a non-zero bi I plus j, right? And because h prime takes 0 to 0, right, only finitely many j give you a non-zero h prime of bi I plus j, right? So it looks a little weird, right? It's sort of a something that like definitely feels kind of contrived when you stare at it, right? It's not the most natural thing in the world, but that's okay, right? Because all we really care about is getting a bijection to this space, and we have a lot of flexibility in doing so. Because we can permute the labels around in any of these factors of n in the product topology, and we can permute the factors of n themselves, right? We have a lot of flexibility in getting here. We just need a way to get there, right? And so maybe one point that I want to emphasize that is possibly a helpful way of thinking about what's going on here is for AF, this mapping that I've described that I claim is a bijection, it describes one entry of the matrix corresponding to Q at a time, right? I plug in a pair of numbers, I and I plus j, and that tells me that the I plus j entry. Okay, on the other hand, when I do this mapping for a locally finite quiver Q, I'm getting a whole row of information about the matrix at a time. I'm saying, hey, fixing my vertex I, right, I'm going to learn all at once everything there is to know about bi I plus j, right? That's all packed into one number, right? So I'm learning all of this all at once. So in some sense, I'm learning a whole row of BQ at a time. It's not technically a full row of BQ. It's more like a full row of like, okay, BQ is a skew symmetric matrix. So it's really like a row after the diagonal, right? So it's not the full thing. If I want the full thing, then I also need to know what's above this row. But for the most part, this is pretty much the full row for I. Okay, cool. So yeah, like I said, these maybe look a little contrived, right? Why these topologies and why use a space like this, right? Why is this an interesting space to use? So let me address the second question first. Why use this space n to the n? It's a nice space. I'm gonna stake my ground on this. This is a nice space. N to the n, it's a separable space, meaning it's got a countable dense subset. In fact, the set of sequences of natural numbers, which are eventually one, that's a countable dense subset. You can check that it's countable, and you can check that it's dense. And it's also completely metrizable, meaning it can be equipped with a metric compatible with the topology, which is complete. And for example, I've given one here. You can define a distance function for distinct f and g, I should say. F and g are sequences of naturals that are distinct. If they're not distinct, define their distance to be 0. But if they're distinct, define their distance to be 2 to the negative, the least index where they differ. Right? And so the longer that f and g agree, the longer an initial segment on which they agree, the closer they are. And so these properties, being separable and completely metrizable, mean that this space n to the n is what's called a Polish space. These are very nice topological spaces. They satisfy a lot of really nice properties, and they're sort of one of the main objects of study in descriptive set theory. Another property of this space that's really nice is that it's got several very nice bases for its topology that we can go back and forth between if we like. One of them is the product basis, right? This is, at the end of the day, it's a product space. It's got the product topology on countably many copies of the discrete space n, so I can use the product basis from that. But it's also got another kind of more natural basis when you try to think about things in terms of like initial segments, which is the initial segment basis, or it's also called the cylinder basis. It consists of cylinder sets. It says, hey, if I've got two functions that share an initial segment sigma, right, then actually, let me phrase it this way. We've got some finite initial segment sigma of a sequence, some finite sequence of naturals, right? That defines a cylinder set and consists of all the sequences extending that sequence, that finite sequence sigma, right? And so this gives me actually a Clopin basis, not just a basis, but a basis of Clopin sets, which is quite nice. And another thing that the recursion theorists really like about this space is that you can view it as the space of infinite paths through the complete tree n to the less than n. This is the set of all finite sequences of natural numbers, and it's got a partial order by extension of initial segments. Okay, so hopefully I've convinced you that this is a nice space and it's got some nice properties that we can work with. If not, I think what's to follow may be a little bit more convincing, but you can take this with a grain of salt if you so choose. So let's turn to the first question, right? Why, out of all the things that we could have like bijected these spaces or these sets LF and AF with, why use this space n to the n? And why are these topologies that we get on LF and AF interesting? To me, I think they're quite natural because of a proposition that I'll talk about in just a second. It provides a very nice understanding for us in terms of like subquivers of convergence. And so for me, it feels like a very natural place to talk about when two infinite quivers look very similar, right? They agree on a lot of, or they agree on a large finite subset in some sense, right? These spaces and their topologies capture that notion in a couple different ways, which we'll see in just a sec. So let me just define a couple of terms. So if I have a quiver with vertex set the natural numbers and some subset of the natural numbers, I think about this as a subset of vertices. I can define the full subquiver, Q restricted to V, given by just saying, hey, let's kill any arrows that have an endpoint outside of the set V, right? We still think about this as a quiver with vertex set n. If you like, you can kill all the vertices that aren't in the set V that you've chosen. It doesn't really matter, but I'm just working with everything vertex set n. So this is the idea of a full subquiver. We just say, hey, let's just take this set of vertices and look at all the arrows that are stuck between two of these guys. There's a looser notion that I didn't have a good word for it, so I called it the overfull subquiver restricted to V. Q restricted to V, superscript over. It has all those arrows that the full subquiver Q restricted to V has, and then some. It's also got any arrows that have just one endpoint in the set V. It's allowed to have arrows to vertices outside of V, which this makes it different from the full subquiver. Right? The overfull subquiver it's over the full subquiver, right? It's more than the full subquiver in terms of arrows. So I've written down there, exactly how you can find these BIJs, find their matrices if you like thinking about the integer matrices. But that's the idea, right? Is the full subquiver we restrict to arrows that are strictly between two things in the vertex set V, and the overfull subquiver having one endpoint in V is good enough. And so with these notions, we can state the following proposition, which is that a sequence of quivers in the space AF converges to a quiver Q in AF if and only if for all finite subsets of the natural numbers, thought about as finite subsets of vertices, the full subquivers Qn restricted to V eventually stabilize. So for large enough n, these full subquivers don't change, and eventually equal this full subquiver of Q restricted to V. Similarly, if we want to say this in LF, it's almost the same thing. We just replace the word full with overfull. So this is a very nice combinatorial characterization of convergence of sequences of quivers in these spaces. Right. So if you thought that this weird bijective stuff was strange, I don't blame you. But I think this proposition justifies sort of what we're doing here. And again, like I said, right, like we have a lot of flexibility. I let you pick whatever bijections you want, so long as h prime of 0 is 0. right? There's a lot of flexibility because you can permute factors and you can permute things in each factor when you're taking this product topology. Um, and that doesn't actually have any bearing on this proposition at all. It's still true, so long as you uh, pick your bijections above as directed. So let's see some consequences of this proposition. Um, First of all, I want to talk about what's going on between these two spaces, LF and AF, right? So um, when I defined what it means for a quiver to be arrow finite, I just said, hey, between any two vertices, you have a finite number of arrows, right? And when I said locally finite, I said, okay, it's arrow finite and then some, right? It's every vertex has finite degree. So in particular, every locally finite quiver on the natural numbers is itself an arrow finite quiver on the natural numbers. So there's a very natural inclusion map, which I've called iota, from LF into AF, right? And it turns out that this map is continuous. This is a continuous map, but not an embedding, which is, maybe when you see that, it's kind of surprising, right? You'd say, oh, LF should just be a subspace of AF, but in fact, it's not, right? It is, in some sense, if we look at the image of LF in AF, the iota of LF, the topology on LF that we get from this guy is strictly coarser, in some sense, than the topology on LF itself. So okay, why is this map continuous? Well, we're working with nice enough topological spaces that continuity is equivalent to sequential continuity. So what we can say is, okay, we should just check that this iota map is sequentially continuous. And this is something that you can check pretty readily. Because if over full subquivers stabilize, right, then, okay, ignore all the arrows that are spilling over and just look at the full subquiver part and say, oh, well, okay, the overfull part stabilized, so does this full part, right? So if I have a sequence of quivers which converge in LF, that means all of the finite overfull subquivers stabilize. So of course, all of the finite full subquivers stabilize, which means the sequence of quivers converges in AF as well. Nice. For the non-embedding part, it's enough to find just an example where the continuity, or sorry, the sequence convergence is not reflected, right? So it's preserved by sequential continuity, but it's not reflected. So what I mean by this is it's enough to find a sequence of locally finite quivers, Qn, which converges to a locally finite quiver Q in the arrow finite topology, but not in the locally finite topology. And so I've done that here for you. The examples are actually pretty simple. The QNs are just taken to be these one arrow quivers that have a single arrow from the vertex 1 to the vertex n. And in the arrow finite topology, this is all well and good because between any two vertices, eventually the number of arrows between those two vertices is 0, right? And that's all that matters in this topology, right? In the locally finite topology, however, right, my vertex 1 is not, it doesn't look like it's stabilizing in any way, right? The full subquiver, the full subquiver, like we see with bigger and bigger vertex sets, like those don't stabilize, right? So this is going to be a little bit of a problem in the locally finite topology. I'm sorry, the not the full subquivers, the over full subquivers. That's the problem we run into in LF. So, okay, so this is a sequence of locally finite quivers which converges to a locally finite quiver in the AF topology, but not in the LF topology. Kind of interesting. Okay, another property that I'll state that relates to these spaces is that the image of LF is a dense subspace of AF. You can, in other words, approximate any arrow finite quiver with a sequence of locally finite quivers. In fact, something stronger is true. You can approximate any arrow finite quiver with a sequence of finite quivers. And when I say finite, here I'm taking a finite quiver to be something which has only finitely many arrows. Of course, the same is true in LF. If we look at finite quivers in the space LF, those are also a dense subspace. In fact, these are countable dense subspaces. There are only countably many finite quivers. And so these witness the separability of these spaces. Okay, concerning mutations, we can view mutations at specific vertices as continuous maps, in fact. So we can, view the mutation at vertex I as a map from LF to itself, or from AF to itself. And by this proposition we just had, right, this is going to preserve the convergence of, or the stabilization of full or over full subquivers. And so in fact it is sequentially continuous and therefore continuous. But of course, as I mentioned before, mutation is an involution, so these are continuous involutions. So okay, they're continuous maps that are their own inverses, so their inverses are continuous. So in fact they're homeomorphisms, which is quite nice. This gives us a group action of the free group on countably infinitely many generators of order 2 on each of these spaces, if you like. And then also, maybe an objection you have to what this notion of closeness looks like in these spaces. Maybe you have an objection to like, oh, this seems to prefer, the smaller labels for vertices. This seems to give more weight to what's happening around vertices 1, 2, 3, and so on. But in fact, by this previous proposition, it actually really does not matter. Every permutation on the labels of the vertices gives you a homeomorphism on these spaces. So there's really no harm in setting up the topologies this way. So, all right. So with that stuff sort of set up, I want to talk now about viewing properties of quivers as subspaces of these spaces LF and AF. So, all right, I got to do a little bit of setting up here, just to tell you about how we're going to talk about how complicated things are. Our yardstick here, our measurement tool, is going to be something called the Borel hierarchy. So this is going to look like some measure theory, but I promise there are no measures involved. I'm sorry if that disappoints you, and you're welcome if it doesn't. But the idea is that we want to be able to measure how complicated subsets of a topological space are. And our way of doing that is going to be by checking, okay, how many like countable intersections or unions do we have to take to get there from like the easiest kind of sets that we can describe, like open sets or closed sets or something. And that's if we're able to do so at all, right? Maybe there are just some sets that we really can't reach by countable means from the open or closed or open sets, right? So we want to know if we can, and okay, if we can, how quickly can we do so? So given a topological space, we can define its Borel sigma algebra, B sub x. This is a family of subsets of x. It's the smallest family of subsets of x, which are contained, which contain all open subsets of x, and it's closed under countable unions and complements. So yeah, that's just the definition we're going to work with here. If you've seen this before, fantastic. If not, don't worry about it too much. And a set is Borel if it belongs to the sigma algebra. Not every set is Borel. This is something I sort of just made a comment about a second ago. We're going to see something that might not be Borel later. That's my bonus section if I have time to get there. But yeah, there's a question I have about that, and so we'll see how that goes. But yeah, importantly, right, I'm using this term, the Borel hierarchy. What is the hierarchy here? Well, this is just saying, hey, let's do this slowly, right? Let's build up this sigma algebra piece by piece, layer by layer. And so we can take sigma 0, 1 to be the family of open sets in X, right? We want to start with sort of the easiest sets we can possibly describe, the open sets and the closed sets. Okay, we're going to let these pi classes, pi 0 alpha, be the families of complements of things that are in sigma 0 alpha, right? So if sigma 0, 1 is the family of open sets, then pi 0, 1 is the family of closed sets. Right? And sigma 0 alpha is the family of sets that we can reach by taking countable unions of things that are in pi classes strictly below alpha. So if we're dealing with finite ordinals, and I'm saying countable ordinals here, and I do mean to include transfinite levels, but if we're just thinking finite levels here, like sigma 0, 3, for example, you can obtain by saying, hey, let's just take countable unions of pi 0, 2 sets, right? And then we're also going to define some other classes, the delta 0 alphas. These are just the families of sets which are both sigma 0 alpha and pi 0 alpha. So this gives us something called the Borel hierarchy. This is sort of our yardstick for measuring things. And so I have a diagram here to sort of maybe give you a little bit of a picture of what this looks like. In Polish spaces, this is what this hierarchy looks like. At the very bottom, we've got some Klopen sets, right? Those are the simplest possible kinds of sets. Those are delta 0, 1 sets. And then just above it, we have our families of open sets and closed sets. And then above that, we have our family of sets, which are delta 0, 2, which those are the things that are both sigma 0, 2 and pi 0, 2. Now, okay, what do those mean? Well, sigma 0, 2 means it's a countable union of pi 0, 1 things. So that means a countable union of closed sets. Or in other words, it's a F sigma set. You have F sigma sets in there. And then dually, pi 0, 2, you can view that as the family of complements of F sigma sets. So they're G delta sets. Or equivalently, you can think about them as the family of countable intersections of sigma 0, 1 sets. So countable intersections of open sets are G delta sets. And so on. This continues for every countable ordinal. This is a transfinite sort of ladder that we have. I'm not going to be worried about the transfinite levels. Everything we're going to see, for the most part, is going to live sort of up to level like 3. So you don't need to worry about what's going on at like stage omega times 2. That's not something that we're going to be concerned with. The big idea, though, is that as we start at the bottom, we have simpler kinds of families of sets, and as we go up, the sets we're describing are more and more complicated. I should also say for uncountable Polish spaces, this hierarchy does not collapse, meaning as you step up every level, these inclusions of families of sets are strict. This is not true in the countable Polish space case. For example, you could take like the integers, right? If you have a discrete space on countably many points, well, okay, every singleton is closed, so every subset is a countable union of closed sets, right? So every set is F sigma, and by taking complements, every set is G delta. So in fact, every set is delta 0, 2, right? So in countable spaces, this hierarchy very much does collapse, but in uncountable spaces, it does not, and that's pretty interesting to us. So let's try and use this, right? Let's try and take this yardstick and try and scale it up against some sets we find out in the wild in these spaces LF and AF. So here's just sort of a laundry list of some properties that you as a combinatorialist might be interested in. Specifically, if you're interested in mutation combinatorics. So the first thing is pretty straightforward. We define what it means for a quiver to be acyclic. This is just when it has no oriented cycles. I'm not saying it has no cycles, period. It's allowed to have cycles so long as I can't walk in an oriented path around them, right? And I write acyc LF and acyc AF to mean the subsets of locally finite acyclic quivers and aerofinite acyclic quivers in the respective spaces. Okay. A quiver is mutation acyclic if I can mutate it finitely many times and get an acyclic quiver, right? And so I write MA-LF for the subspace of locally finite mutation acyclic quivers, and MA-AF for the subspace of aerofinite mutation acyclic quivers. And sort of by definition here, you can think about these as countable unions of images under the closed sets mu sub I bar of the closed set acyc. Depending on what space you're working in, you put the appropriate subscripts and everybody's happy. I'm sorry, appropriate superscripts and everybody's happy. Okay, another thing is that we can define what it means for a quiver to be finite. Now, I know you might be squinting in this and saying like, wait, aren't we working with quivers with vertex set the natural numbers? Yes, we are. But as long as there are finitely many arrows, for all intents and purposes, as far as mutation is concerned, the quiver behaves like a finite one, right? If you mutate an isolated vertex, literally nothing happens, right? So if I only have finitely many arrows, in other words, I have co-finitely many isolated vertices, nothing bad is going to happen, right? So I might as well think about it as a finite quiver. Okay, I can also talk about connected quivers, and I have to pull a similar trick here because, like, okay, isolated vertices don't really do anything. So I'm actually kind of okay with isolated vertices getting in the way or not getting in the way of connectedness, right? I say that a quiver is connected if it has at most one non-trivial connected component. So when I say non-trivial connected component, I mean, you know, what you would think, right? A connected component consisting of at least one arrow, right? I'm okay with isolated vertices up the wazoo, right? You can take as many of those as you want. That's not going to change the answer to the question, is this quiver connected? And then finally, I can also talk about subspaces of the squares of these spaces, LF squared and AF squared, which I should note that if you take n to the n cross n to the n, it's homeomorphic to n to the n again. So the homeomorphism type hasn't changed, but I'm still writing it like this just for sort of readability. Like it doesn't really make sense to try and pretend that these are copies of the original space. Um, we can't really interpret it very well in that case. So anyway, if I have two quivers, Q1 and Q2, I declare them to be mutation equivalent if there's some finite sequence of mutations. I should have said finite there. If there exists some finite sequence of mutations that gets me from one to the other. And so I write these as sets of pairs in the respective spaces, LF squared and AF squared. Okay, and when I say this, I mean, I'm literally writing down the binary relation defining the equivalence classes of mutation equivalence. Okay, so these are just some properties I'm going to throw out here. Let's see where they live in this Borel hierarchy. So, all right, here it is, sort of a pretty heavy slide. Let's just focus on the left side for right now. Here's that Borel hierarchy again. In, I don't know if it's magenta or like a fuchsia of some kind, pink. I've sort of drawn just a bunch of properties or sets of pairs, really subspaces of some spaces, and sort of pointed to, hey, I know they're in this class, right? So anytime you see a superscript, that's going to tell you more specifically what space I'm thinking about. If you don't see a superscript, it means it applies to either of the spaces LF or AF, right? So for example, I see Finn over on the left, it's pointing at sigma 02. When I'm saying that, I'm saying, hey, I know that the set of finite quivers in LF or in AF, it doesn't matter, is going to be a sigma 02 set, right? And okay, this is nice. I can also say these kinds of things for, mutation equivalent, the set of mutation equivalent pairs of quivers, right? I know that this is also sigma 02. But I've also, in this case, drawn a little purple arrow down to delta 02, because in fact, I'm not sure whether or not it's down there, right? This very well may be a delta 02 set, right? Not just sigma 02, but delta 02. Of course, being delta 02 automatically means you're sigma 02 by this inclusion sort of ladder, but right, I don't know. I don't know if this set is pi 02, right? So I sort of have some loose ends here. And if anybody wants to help me out with that, or if you have any ideas about how to show these kinds of things, please let me know. I'm pretty certain that actually none of these loose ends are actually, like, I'm pretty sure all the pink arrows I've drawn are sort of like the best you can do. But, jury's out on that one. And then, okay, I have some other properties that I've listed there as well. Sometimes, depending on which space you're in, some things are more complicated in one space than the other. Just by virtue of the fact that there's a continuous map from LF to AF. In fact, if I have one property that makes sense to define in both spaces, it's always going to be at least as complicated in AF as it is in LF, because you can show that these classes are closed under continuous pre-images. But anyway, right? So like, for example, it is strictly more complicated to say that a specific vertex I is an isolated vertex for a quiver in the aerofinite topology than it is to say so in the locally finite topology, right? So that's kind of interesting. And so over on the right, I have just sort of a sketch of an example of how you would go about showing some of these things. I did it for the locally finite set of acyclic quivers and the locally finite set of mutation acyclic quivers. I've gone through sort of the parts of like, okay, I want to show that acyc is pi 01, it's closed. And I want to show it's not open, meaning it's not delta 01. And then, okay, that takes care of the acyclic part. Then the mutation acyclic part, I want to show that it's sigma 02, or that it's an F sigma set. This sort of follows by definition once you know that acyc is closed, right? Just by using that union over the images of finite mutation sequences applied to acyc, gives you LF. I'm sorry, gives you MA. Right, this is sort of immediate. It is literally, as when you write it down like that, a countable union of closed sets. And you can check that it's not open by using, in fact, the bare category theorem. So I highlighted that just because I think it's really fun that you can use this very interesting topological theorem to say something about how complicated a property of infinite quivers is. I think it's really cool when you have that kind of crossover. And then also, of course, you want to show that the set of mutation acyclic quivers is not closed, right? Because I'm claiming that MA is at least delta 02. So, right, I have sort of this mess of a web of arrows drawn over here. And so I know it might be a little challenging to decipher as I'm sort of going through it. But the idea is, right, as I'm pointing to things on the left, right, the things on the right are saying, okay, give me an upper bound, give me a lower bound, and prove it. Right? In fact, I like this example of showing that MA is not closed in the locally finite topology, because what does that mean? That means I need to give you a sequence of mutation acyclic quivers, which are locally finite, which converges to a locally finite quiver in the locally finite topology. But that limit quiver is not itself mutation acyclic. And so here, if you know what it means to be a type A tilde 1n, or I guess 1n minus 1 quiver, that's what I've got for Qn here. Those guys are mutation acyclic. You can mutate them infinitely many steps to an acyclic quiver. And then Q itself, it's this limit of these guys, but it's not itself mutation acyclic, which is kind of interesting. So, right, this is just an example on the right of sort of a sketch of how you would sort of establish some of these things. Okay. So just quickly shifting gears a little bit, I want to talk now about infinite mutation sequences. I'll go through this kind of quickly, but the idea is pretty simple, right? We care about finite mutation sequences all the time, but we're working in a topological space. So what would happen if we, took an infinite mutation sequence and sort of looked at a pointwise limit of it, right? We take an infinite mutation sequence and we try to apply it to a quiver, and to test whether or not it converges, we just look at, okay, I apply the finite initial segments of this mutation sequence to the quiver, and does this sequence of quivers converge? Right? So that's the idea here. So I'm going to identify infinite mutation sequences with sequences of natural numbers. Just by saying, hey, mutate at this natural number at this time. Right? Okay, and so given such an infinite mutation sequence, and given a locally finite quiver or an arrow finite quiver, right, the definitions are symmetric. We say that that mutation sequence converges on the quiver, and I write it with this little mu I bar of Q down arrow. I write this down arrow to say it converges. If the sequence of finite partial mutation sequences applied to this quiver converges in the respective space. And I've got this notation d sub lf superscript down arrow of mu sub I bar. Replace the lf with an af, and you get something symmetric. This is the domain of convergence of the mutation sequence mu sub I bar in the space lf, right? This is the set of all quivers on which mu sub I bar converges, right? So this is sort of going to be a set that I want to study. If you like, you can think about this as, in a lot of ways analogous to the convergence of power series, right? An infinite mutation sequence will converge on a quiver if and only if every tail of that mutation sequence converges on, I guess you have to change the initial quiver by the finite initial sequence that you have chopped off to create your tail. But right, so you can get something like that. Yeah, there's sort of an interesting analogy there, and you can kind of use this in some arguments to build some intuition for these objects. There are differences, given a mutation sequence, there are differences in these domains of convergence, even among the locally finite quivers. For example, this quiver here, this infinite line quiver with an arrow from 1 to 2, an arrow from 2 to 3, and so on, the mutation sequence 2, 3, 4, and so on, this converges on this quiver in the AF topology, but not in the locally finite topology. So even among locally finite quivers, these domains of convergence of a fixed mutation sequence can differ. So hard question. Given a mutation sequence, an infinite mutation sequence, can we completely characterize these domains of convergence in the LF topology, the AF topology? And that's a hard question. I don't know. I'm guessing no. Like, that seems really difficult. But you can deal with some specific kinds of questions, and you can deal with some specific kinds of cases of mutation sequences and get some answers. And so what I want to present is exactly that. when we specifically restrict to the question of, okay, when are these domains of convergence dense? When are their complements dense? Or in other words, to say the complement is dense means you have empty interior, right? So I want to ask about the density of these domains of convergence and whether or not their interiors are empty. So that's what we're going to talk about here. So the AF case, it's not too bad. There's a little flowchart here that I have. Essentially, what happens is no matter what, first of all, your domain of convergence always has empty interior. Or in other words, the domain of divergence is dense, right? There's a dense set of quivers on which your given mutation sequence diverges. No matter what, it does not matter what your mutation sequence is. And this boils down to one of two things happening. Either there is a vertex which is mutated at infinitely many times, and you can use that to show that you have a dense set of quivers which diverge, or on which this mutation sequence diverges. Or you mutate at infinitely many vertices, and you can cook up examples in a initial segment extending way to produce things which diverge, right? So the interesting question here to ask is, okay, well, this domain of convergence always has empty interior. What about its density, right? When is it dense? It turns out it's dense if and only if there is not a vertex which appears infinitely many times in this mutation sequence. If there is, you're out of luck, right? It's going to be a dense domain of, I'm sorry, a non-dense domain of convergence, right? So it's kind of sparse in some sense. If there is not a vertex appearing infinitely many times, well, okay, you still have a dense domain of divergence, but now you have a dense domain of convergence too. And so I've drawn this here in this little flowchart. And you might say, okay, why do we need the flowchart? The theorem was good enough, as stated. You'll see why on the next slide, mostly just as a point of comparison to the locally finite case. But yeah, so the main tools here, they're not too bad. If you have a vertex in your quiver which has some number of arrows attached to it, it's not isolated. If this vertex is mutated at infinitely many times, then like no matter what, the mutation sequence is going to diverge on this quiver. It does not matter what the rest of your quiver looks like. Just having arrows connected to this vertex is enough. And then I also kind of make liberal use of this specific quiver that I've drawn here. It's got two privileged vertices, 1 and 2, which have arrows either to every other vertex, 3, 4, 5, so on, or from every other vertex. And so then you can sort of take this tail of a mutation sequence idea that I mentioned sort of when I was talking about the power series analogy, and assume in some cases, without loss of generality, that 1 and 2 are not mutated at all. And then you can say, oh, well, if I mutate at 3, 4, 5, blah, 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 right? I'm always changing the number of arrows between 1 and 2. That does not ever settle down. So the full subquiver supported on 1 and 2 does not stabilize, right? So this is sort of the idea there. You can use this tool to kind of help you force divergence in a dense way. Okay, so here's the LF case. Looks a lot worse, right? It's because it is. I'm not going to go through every little bit of this here, but I do just want to take a second to sort of appreciate how much more complicated this is than the previous case of a single yes or no question, right? Here we have to ask several questions, right? We got to ask, is there a vertex appearing in this mutation sequence infinitely many times? Okay, if there is, right, then I have to ask another question. How about the vertices which only appear finitely many times? Is this subsequence of finite length? Okay, yes or no? All right. Yes, there exist infinitely many vertices appearing infinitely often, right? You can get into the weeds with this. It's very intricate in some ways. I was not expecting this when I originally asked this question. I was like, okay, well, this is what it looks in the AF case. Surely it's not too far away in the LF case, but it is. It's a lot different. And so you have 4 sort of different outcomes here. Yeah, they're quite messy. That's what I'll say about that. But yeah, if you're curious, absolutely ask me more about this. But yeah, a lot going on here. There's maybe a comment I'll make about the strategy that goes into this proof is we really try to force divergence however we can. And what that usually comes down to is one of 2 ways. Either we try to blow up the number of arrows between any two fixed vertices, or at least make it fail to stabilize, or we try to force our way out of LF into something bigger, into AF, right? We try to force a vertex to look like it's going to blow up and have infinite degree, right? These are sort of the strategies that we like to use here. And then also there's some more casework that isn't in this picture that I'm showing you here. Sometimes in some of these cases, you have to break down into like, are there an infinite number of vertices which are mutated at an odd number of times in your sequence? If so, do something. If not, then there are an infinite number of vertices mutated at an infinite number of, an even number of times, right? So you have to do something there, right? And it just gets quite messy. So I think this is a lot of fun. I think this is a pretty cool kind of theorem to state. So then, yeah, maybe just with one more minute, I'll say, what if we tried to merge these stories, right? We've talked about density and interiors for these domains of convergence. What if we tried to talk about their Borel complexity? With a little bit of work, it's not too bad. You can show that these sets are at worst pi03. If you like to think about things with the F sigmas and G deltas and stuff, this is F sigma delta sets, right? It could be lower, right? But right, some of these sets are less complicated, right? Some of the cases, like the domain of convergence in LF, in one of the cases was all of LF, right? So, obviously in some cases, like the sets are simpler than pi03. So, right, this is interesting. But what if we try to sort of drop references to specific mutation sequences? Well, this is hard, it turns out. So I have an open question that I just want to pose and maybe make a slight comment on before I finish. And this is, if we try to take the analog of infinite mutation equivalents, right? Take pairs of quivers for which there is some infinite mutation sequence converging on the first one, giving you the second one, right? What does this set of pairs look like in LF, for example, or in AF? You could do it in either space. I don't even know if this set is a Borel set. This is tricky. So if it's a Borel set, that would be very interesting because that means there is some like symmetry or something in the mutation combinatorics that you can exploit to show so, right? It means there is some simplification you can make based pretty much entirely on quiver mutation combinatorics. And if this set is not Borel, then that means that quiver mutation combinatorics are very hard on the infinite scale, right? I think that would be very interesting as well. What I can say is that if they're not Borel, they're very close to being Borel. They're like the next best thing. They're called analytic sets. They're continuous images of Borel sets in some other Polish space. Formally speaking, that's what they are. They're pretty darn close to Borel sets. Particularly if their complements are also analytic, then that means they are Borel by a certain theorem called Suslin separation theorem. So I don't know. I think that'd be very interesting if they were Borel. And if they are Borel, how complicated are they, right? Place them in the Borel hierarchy. If they're not, right, I think that'd be very interesting as well. Yeah, so I think that's what I'll say about that. And yeah, that's what I've got. So thank you everybody for your time and I'm happy to answer any questions.
All right, any questions for Ben? I have a couple.
Yeah.
So I guess maybe this is like the natural question. Is there any like clustery type thing on these infinite quivers? Like, can you define some sort of cluster algebra like object?
So
Or
this is a good question. I was thinking about this earlier in the summer. I was trying to think about like, okay, here we have like quivers whose vertices are labeled with natural numbers. What if we tried to do something where we labeled vertices with like cluster variables, right? You would have to change the labels of the vertices as you mutate, which you don't do here. You just keep them static. So that's a little bit of an obstacle, but I think I came up with something that kind of made it work. But I don't know. It also kind of felt like reinventing the wheel a little bit. I was like, I don't know how interesting this is or like what you're doing here in this topological language that you can't just say otherwise as far as the cluster variables go. But yeah, that's definitely something I'd be interested in. Yeah.
also had another question. So is there any relation between this Borel hierarchy and the like I've heard it described like the polynomial hierarchy in like computational complexity theory?
Yes, and I don't really know too much about what it is. There are definitely a lot of analogies. I think when people write down the like classes, the complexity classes for things in like the polynomial hierarchy, I think they also just like use like sigma one, sigma two, pi one, pi two. Like they use the same symbols and they put a superscript p on them. Um, in some cases, I don't know. I think they use like different superscripts depending on what like complexity classes they're looking at. But um, I think it's mostly an analogy as opposed to like a formal connection. But I'm honestly not very sure. That's not so much something that I'm super familiar with, unfortunately.
Because I know there are a lot of like theorems in that area where it's like this is true unless the polynomial hierarchy collapses. So I'm
Yeah,
wondering if
yeah,
there's maybe some like define some weird topological space where the points are computational problems or something like that, and then
yeah.
there's something weird. I don't know.
I think the way that I would think about it is this is like a higher type kind of analog of what's going on down there with computational complexity. Like this is all the way up on the level of like sometimes like models of set theory. There are some things you can say about like sets in the Borel hierarchy and like sets just beyond the Borel hierarchy, like analytic sets or co-analytic sets. Um, there are some things you can say about like analytic and co-analytic sets that are independent of ZFC. That's something that's a little scary to me actually because I'm trying to think about this set of pairs of quivers that I would love if it were Borel. I would love if it weren't. But there's a secret third option. Uh, Not really. There's okay. It's still one of those two options, but there's sort of an in between thing that can happen in some models of ZFC and not in others. And so like I don't know. I'm just really hoping it's not that. Um, but yeah, so it's like I don't know. I don't know if it's quite a one to one thing, but like there are some like ZFC independence results that like to me smell like a hierarchy collapsing versus not collapsing. It's more like a yeah, it's like determinacy things, but I don't know. It's a little bit different, I think.
Thanks. Any other questions? If not, I guess we can stop the recording. Maybe